everyone. Today we will discuss end sem examination question paper of numerical analysis and loop. So first question is explain the fixed point iteration method by demonstrating the root of equation fx equals to x square minus x minus 1 equals to 0. Demonstrate graphically convergent, divergent and loop situation while choosing g of x. Prepare a table for various choice of g of x and decide the g of x that is convergent for given x. So, the fixed point iteration method is an iterative numerical method used to find root of a given equation. It involves finding a function such that the equation f of x equals to 0 can be written in a form x equals to g of x. The idea is to start with the initial guess of x and then repeatedly apply the function g of x to update the value of x until convergence is achieved. Let's demonstrate the fixed point iteration method for the equation fx equals to x square minus x minus 1 equals to 0. We need to find a suitable function g of x such that x equals to g of x. So, to demonstrate graphically convergent divergent loop situation, we will choose different function g of x and observe their behavior. Let's choose g of x equals to x plus 1. In this case, the updated value of x in each iteration will be x equals to x plus 1. We start with initial guess, let's say x0 equals to 1. So iteration 1 will be x equals to x0 plus 1 which is equals to 1 plus 1 which is equals to 2. Iteration 2 will be x2 equals to x1 plus 1 which is equals to 2 plus 1 which is equals to 3. Now third iteration is x equals to x2 plus 1. So x2 is 3. So 3 plus 1 equals to 4. And we will continue so on. As we can see, the value of x keep increasing and diverge to infinity. This situation is known as divergent case. Now let's choose g of x equals to x square minus 1. For this choice, the updated value of x in each iteration will be equal to x equals to x square minus 1. Starting with an initial guess, x0 equals to 1. Iteration 1, x1 equals to x0 square minus 1 which is equals to 1 square minus 1 which is equals to 0. Iteration 2 is equals to x2 is equals to x1 square minus 1 and x1 is 0, so 0 square minus 1 which is equals to minus 1. Iteration 3 is x3 equals to x2 square minus 1. x2 is minus 1, so minus 1 square minus 1 which is equals to 0. In this case, the value of x oscillate between two values 0 and minus 1 in a loop. This situation is known as loop case. Now lastly, let's choose g of x equals to 1 plus 1 upon x plus 1. Taking x0 equals to 1 as an initial guess. Iteration 1 will be x1 equals to 1 plus 1 upon 1 plus 1 which is equals to 1.5. Iteration 2 equals to x2 equals to 1 plus 1 upon 1.5 plus 1 which will be almost equals to 1.6667. Iteration 3 is x3 equals to 1 plus 1 upon 1.6667 plus 1 which is almost equals to 1.6. Iteration 4 is x4 equals to 1 plus 1 upon 1.6 plus 1 which will almost equal to 1.625 and so on we will continue. In this case, the value of x approaches a specific value approximately 1.618 which is a golden ratio. This situation indicates convergence and the function g of x equals to 1 plus 1 upon x plus 1 is convergent for the given equation of f of x. To summarize our observation, here is the table. Functions were g of x equals to x plus 1, g of x equals to x square minus 1 and g of x equals to 1 plus 1 upon x plus 1. So for x plus 1 it was divergent. For x square minus 1, it was a loop behavior, and for 1 plus 1 upon x plus 1, it was a convergent behavior. Therefore, for the given equation f of x equals to x square minus x minus 1 equals to 0, the function g of x 1 upon x plus 1 is a convergent choice. Now, next question. Write an algorithm for finding the root of f of x equals to x square minus x minus 1 equals to 0 using fixed point iteration method. Certainly, the fixed point iteration algorithm is a simple iterative method for finding root of a function. Here's an algorithm to find the root of function f of x equals to x square minus x minus 1 equals to 0 using fixed point iteration. First, we will start with an initial guess for the root. Let's call it as x0. Next, define a function g of x that transforms the original equation f of x equals to 0 into the form x equals to g of x. In this case, we can rewrite the equation as g of x equals to x square minus 1. Set an error tolerance value epsilon to determine the accuracy of result. Fourth step, set a maximum number of iteration, max iteration to avoid infinite loops. Now, initialize the iteration counter, iter dash count to 0. While iteration counter is less than maximum iteration, do the following. First, compute the next approximation of the root, which is x next is equals to g of x0. Second, if the absolute difference between x next and x0 is less than epsilon, stop iterating and return x next as the root. Third, update x0 with new approximation. x0 is equals to x next. Fourth, increment in iteration count by 1. If the algorithm reaches this point without finding a root, it means the maximum number of iterations were exceeded. In this case, you can either terminate the algorithm without a result or return last approximation as the best guess for the root. That's it. The algorithm will keep iterating until either the root is found within desired accuracy or maximum number of iteration is reached. So this is the algorithm for iterating method. Now, next question. Write the output of the program of question 2. So previous questions का output लिखना है हमें. So to demonstrate the output of a program, let's assume the initial guess for the root x0 is 1.5 and the error tolerance is set to 0.0001 and the maximum number of iteration is 20. So here step by step output of the program. We will calculate each iteration. So first iteration will be x0 is equals to 1.5. We have guessed this root. X next is equals to g of 1.5, which is equals to 1.5 whole square minus 1, which is equals to 1.25. Second iteration, third iteration will continue till 13 iteration. Then the program stop at 13 iteration because the absolute difference between x next and x0 is reached. Therefore, it will stop at 13 iteration. Now, next question. Write an algorithm for Gauss elimination method with pivot. So here is the algorithm for Gauss elimination method with pivoting. First, input the system of linear equation as the argument matrix A, B, where A is coefficient matrix and B is the constant vector. Initialize a variable n to the number of equation in the system. For k is equals to 1 to n minus 1, do following. Find the row P such that absolute value of A of P k is maximum among the value of A of k k, comma A of k plus 1 k, and so on till A of n k. Swap row k and p in both A and B matrices. For I is equals to k plus 1 to n, do following. Calculate the factor of factor m, which is equals to A of ik divided by A of kk. Update ik is equals to 0. For j is equals to k plus 1 to n, update aij equals to aij minus m times a of kj. Update b of I, which is equals to b of I minus m times b of k. Now back substitution. Set x of n equals to b of n by a of n. For I is equals to n minus 1 to 1 to following. Set sum equals to 0. For j is equals to 1 plus I plus 1 to n, calculate sum equals to sum plus a of ij times x of j. Set x of I is equals to b of I minus sum by a of ii. Output the solution vector x. This algorithm performs Gaussian elimination with pivoting to transform the argumented matrix into upper triangular form. The pivoting step ensures that the largest absolute value are to avoid division by small number and increase numerical stability. Finally, the back substitution step solves the variable by substituting value from the last row back into earlier row. We should note that in step third of A, if all the value of A of k plus 1 and so on are already 0, it means that system may have multiple solution or no solution exists depending on the value in the B vector. Question: solve the system of equation using iterative method accurate to 4 significant digits. So we need to solve these three equations using iterative method. To solve the system of equation using iterative method, we need to rewrite the equation in the form of x equals to g of x and iterate until convergence is achieved. Let's arrange the equations. Equation 1 will be 20x1 plus x2 minus 2x3 is equals to 17. Equation 2 is 3x1 plus 20x2 minus x3 equals to minus 18. And third equation is 2x1 minus 3x2 plus 20x3 is equals to 70. We can write this equation in form of x equals to g of x. So x1 is equals to this, x2 equals to this, x3 equals to this. Now we can use this equation in the iterative method. Let's choose an initial guess for x1, x2 and x3 and then update the value until the convergence is achieved. Okay. So let us assume the initial value of x0 equals to 1, 1, 1. Iteration 1 is x1 is equals to 17 minus 1 plus 21 divided by 20, which is 0.9. x2 minus 18 minus 31 plus 1 divided by 20, which is equals to minus 0.95. Third, x3 is equals to 17 minus 21 plus 3 times minus 0.95 divided by 20, which is equals to 0.935. Now we will see iteration 2. Continue and so on. Continuing this process, we iterate until the convergence is achieved. Let's perform few more iterations. So iteration 3, we will get these values. Iteration 4, we will get these values, which are almost same. We can see that. At fourth iteration, we observe the value of x1, x2 and x3 remains same. This indicates convergence. Therefore, solution of system of equation accurate to 4 significant digits is approximately these, which is x1 is 0.9362, x2 is minus 0.9362 and x3 is 0.9362. Now next question. Write 4 disadvantage of Gaussian elimination and 3 advantage of iterative method over elimination method. Okay. So while Gaussian elimination method is widely used technique for solving system of linear equation, it does have some disadvantage, which are: first, computational complexity. The Gaussian elimination method has a computational complexity of O(n) cube, where n is number of equation, which means that as the size of system increase, the time required to solve it grows rapidly. For very large system, this can be computationally expensive and time consuming. Second disadvantage is numerical stability. The method can suffer from numerical instability when dividing by small pivot value. If the pivot value are very close to zero or become zero during elimination process, it can lead to division by very small number or even division by zero, resulting in numerical error or inaccurate solution. This is especially true when working with ill-conditioned or nearly singular system. Third disadvantage, round-off error. Due to accumulation of round-off error during arithmetic operation involved in the elimination process, the computed solution may be deviated slightly from the exact solution. These errors can propagate and affect the accuracy of results, especially for the system that are sensitive to small perturbation. Next, limited parallelism. The Gauss elimination method does not naturally lend itself to parallel computation. The computation for each row depends on the previous row result, making it difficult to efficiently distribute the workload across multiple processors or core. As a result, it may not fully leverage the potential benefit of parallel computing. Now we will talk about the advantage of iterative methods. Iterative method for solving system of linear equation have several advantages, making suitable for certain scenario. Memory efficiency. Iterative method often require less memory compared to direct method like Gauss elimination. Instead of storing the entire augmented matrix, iterative method only requires storage for the current approximation vector and few additional variables. This makes them more memory efficient, especially for large scale system. Second, computational efficiency. In some cases, iterative method can be more computationally efficient than direct method. This is particularly true when solving sparse system, where most of matrix elements are zero. Iterative method can exploit the sparsity of the matrix, reducing the number of arithmetic operations required and potentially improving efficiency. Third, convergence control. Iterative method provide control over the convergence behavior. The iteration process can be terminated based on the convergence criteria, allowing for fine-tuning of the trade-off between solution accuracy and computational cost. This is particularly useful when solving systems with specific requirements such as finding an approximate solution within a certain tolerance. So these were the advantages and disadvantages. Now, next question. Obtain the estimate of the missing figure using delta E operator in the following data. So we have data as 2.0 and 0.135, 2.1 and dash, 2.2 and 0.111, 2.3 and 0.1, 2.4 and dash, 2.5 and 0.08, 2.6 and 0.074. To estimate the missing figure using the delta and E operator, we need to identify the pattern in the available data and use it to interpolate the missing values. Let us calculate the delta difference between consecutive x value and y value. So for delta x, we will take this x value and this x value. So 2.1 minus 2 is equals to 0.1. Now we will take x value. So we will take this value and we will consider it as 0. So we will get 0.135 minus 0 equals to 0.135. Now we will take this value and this value. So we will get minus 0.024. Now we will see this value and this value. So we will get minus 0.011. Now we will see this value and this value. So we will get minus 0.02. Now we will take this value and this value. So we will get minus 0.006. Now let's calculate the E values, which are the ratio between consecutive delta y and delta x. So E1 is delta y1 upon delta x. So it will be 0.135 upon 0.1. So it will be 1.35. E2 will be minus 0.24. E3 will be minus 0.11. E4 will be minus 0.2 and E5 will be minus 0.06. Now we can use E values to interpolate the missing figure. For the missing figure 2.1 comma dash, to estimate the Y value at x equals to 2.1, we use E1 value. E1 is 1.35, missing figure is 2.1 comma dash. The previous Y value plus E1 into delta x. So 0.135 plus 1.35 into 0.1, which will be equal to 0.27. Similarly, we will calculate for this 2.4 comma dash value. So we will get answer as 0.08. Therefore, the estimation for the missing values are 0.1 comma 0.27 and 2.4 comma 0.08. Write an algorithm for Lagrange's inverse interpolation method. So the Lagrange inverse interpolation method is used to find the value of independent variable x given a specific value of dependent variable y in an interpolation problem. Here's the algorithm for Lagrange interpolation method. First, input the set of data points xi, yi for I is equals to 0 to n, where n is the number of data points. Input the desired value of y denoted as y target. Compute the Lagrange coefficient for each data point using the formula Li is equals to y target minus yj divided by yi minus yj for j is not equals to I, where the product is taken over all data points of x of j comma y of j for I is not equals to j. Now compute the value of x using the formula x equals to sigma xi into Li for I is equals to 0 to n. Output the value of x as a result. This algorithm utilizes Lagrange interpolation formula to compute the value of x that correspond to the given value of y. The Lagrange coefficients are commutated based on desired value of y target and y value of data point. Finally, the value of x is obtained by summing the product for each xi with its corresponding Lagrange coefficient. It is important to note that Lagrange inverse interpolation method assumes a one-to-one mapping between x and y, and the data points are well behaved. If the conditions are not met, the method may produce inaccurate result or encounter difficulties. Now, next question. Evaluate the 1 upon 1 plus x square using 3-point Gauss quadrature formula for the given abscissa and weight. T1 equals to 0.77459667, T2 is equals to 0, T3 equals to minus of T1, W1 equals to minus 0.555556, W2 is equals to 0.8889 and W3 is equals to W1. So let A and B, let A is equals to 0 from here and B is equals to 1. So x equals to B minus A by 2 times t plus b plus a by 2. Putting the value of a and b, we will get x equals to 1 plus t upon 2. So we will differentiate it. So d of x is equals to dt upon 2. Now substituting the value of x and dx in f of x. So f of t is equals to integration minus 1 to 1 2 upon 4 plus 1 plus t times 2 dt. So f of t is equals to 0.555556 times f of minus 0.7745 plus f of 0.7745 plus 0.88889 of f of 0. So we will get the answer as 0.78527. This is the final answer of the integration. Now, next question. Derive Simpson's rule using Newton's code formula. So to derive Simpson's rule using Newton code, we start with general formula for Newton code's integration. So the general formula for Newton code is this, where a and b is the interval of integration and f of x is the integrand, and h is equals to b minus a upon n is a subinterval with n evenly spaced point, and y0, y1, y2 till yn are the function values at these points. Now let's consider Simpson's rule, which uses a special case of Newton codes integration with n is equals to 2. So integration a to b f of x dx is equals to h by 3 bracket y0 plus 4 times y1 plus y2. To derive this rule, we need to evaluate the integral of f of x using 3 points a, b and the midpoint m, which is equals to a plus b by 2. Let's denote the function values at these points, and f of a is equals to y0, f of m is equals to y1 and f of b is equals to y2. Now, using the general Newton code formula, we can express the integral as this. Okay, since n is equals to 2, we have two subintervals. So h is equals to b minus a upon 2. Substituting these values, we get this integration a to b f of x dx is equals to b minus a divided by 6 bracket y0 plus 4y1 plus 2y2 plus y3. Now we need to determine the function value y0, y1, y2 and y3 in terms of the given point a, b and m. Using the given point and applying the function value to our equation, we have y is equals to f of a, y1 is equals to f of m, and y2 is equals to f of b. To find y3, we can consider second subinterval m comma b and divide it into two equal parts. mb is equals to m comma m plus b minus m by 2 plus m plus b minus m by 2 comma b. Since b of m by 2 is equals to h, we can rewrite second interval as m comma m plus h. Now using midpoint rule for the subinterval, we get integration m comma m plus 1 f of x dx is equals to h by 2 f of m plus f of m plus h. Substituting ym, which is f of m, and y3, which is f of m plus h, into our integral expression, we will get this expression. Now substituting all the values of y0, y1, y2, y3 into our Newton codes formula, we will get this. No, in Newton code formula, which is this, we will get this value. We will simplify this equation further. So we will get integration of a to b f of x dx is equals to b minus a upon 6 f of a plus 4 f of m plus f of b plus 4 fm f of m plus h. We have derived Simpson's rule using Newton's code. Now next question, write an algorithm to evaluate Widow's law for given problem in question number 8 with n equals to 6. So we have to discuss Widow's rule with previous question, and n is given as 6. Widow's rule is a numerical integration method used to approximate definite integrals. Here the algorithm to evaluate Widow's rule for the problem of integrating 1 upon 1 plus x squared dx with n equals to 6. Input the lower limit a and the upper limit b of the integration. Calculate the step size h using the formula h equals to b minus a upon n, where n is number of subintervals. Set the initial value sum is equals to 0 and x equals to a. For I is equals to 0 to n minus 1, do the following. Calculate the subinterval boundaries. xi is equals to x plus I into h. xip1 equals to x plus I plus 1 into h. Calculate the weight of Widal's rule. W1 is equals to h by 2, W2 is equals to h by 6. Evaluate the function at subinterval boundaries. F of xi is equals to 1 upon 1 plus xi square. F of xip1 is equals to 1 plus 1 upon 1 plus xip1 whole square. Update the sum using Widal's rule. Sum is equals to sum plus W1 into this plus W2 into this. Output the approximate value of integral as sum. In this algorithm, the definite integral of 1 upon 1 plus x square is approximated using Widal's rule with n is equals to 6 subinterval. The integration interval a to b is divided into smaller subinterval and the function is evaluated at the boundary of each subinterval. The weight of Widal rule are applied to these evaluations to compute approximate integral. Note that as the number of subinterval increases, the approximation tend to become accurate. However, it is important to choose an appropriate value for n based on the desired precision and the characteristic of the function being integrated. Now, next question. Write an algorithm for Range-Kutta fourth order method. Range-Kutta method is a numerical technique used to solve ordinary differential equation. Here, algorithm for fourth order Range-Kutta method. Input the initial condition, the initial value of independent variable x0 and the initial value of dependent variable y0. Input the step size h and the number of steps n for the desired interval. Set x is equals to x0 and y is equals to y0. For I is equals to 1 to n, do following. Calculate the intermediate values. x1 is equals to h into f of xy. k2 is equals to h into f of x plus h divided by 2 comma y plus x1 divided by 2. k3 is equals to h into f of x plus h divided by 2 y plus k2 divided by k4 is equals to h into f of x plus h comma y plus x, k3. Now update the value of x and y. X is equals to x plus h and y is equals to y plus k1 plus 2k2 plus 2k3 plus k4 divided by 6. Output the value of x and y for each step. In the above algorithm, f of x and y represent the derivative of y with respect to x, which is typically given in the ODE problem. The Range-Kutta method estimates the value of the dependent variable at each step by considering weighted average of the deviation at different intermediate points. The fourth order Range-Kutta method provides a good balance between accuracy and computational complexity. Note that the algorithm assumes a single ODE. For system of ODEs, the method needs to be modified accordingly. Additionally, the step size h should be chosen carefully to ensure the accuracy and stability, considering behavior of the ODE and desired level of precision. Now, next question. Apply predictor corrector method to solve dy by dx is equals to minus xy, where x of 0 is equals to 1 in steps of 0.1 up to y 0.2. So yn plus 1 is equals to yn plus 2h f of xn plus 1 yn plus 1. And ये predictor, this is for predictor. Now for corrector, y is equals to n plus 1 is equals to yn plus h by 2 f of xn yn plus f of x plus n x n plus 1 yn plus 1. By this method, k1 is f of xi yi, k2 is f of xi plus h by 2, comma yi is plus k1 h by 2. Now, k is equals to k1 plus k2 divided by 2. Yi is plus 1 is equals to yi plus k of h. Hence, y 0.1 is equals to 0.9975. Y2 is equals to y0 plus 2h f of x 0.1, y 0.1. This is predicted. Now, y 0.2 is equals to 1 plus 2 into 0.1 into minus 0.1 into 0.9975. So y of 0.2 is equals to 0.98005. Now for y 0.2, we will calculate the using predicted formula, but this value. So we will calculate, so we will get 0.982712, which is the correct value. We can apply corrector formula again for accurate value by putting this corrected value as predicted value in the corrected formula. So we can again using this predicted formula and this corrected value, we can find a proper accurate value of x. Now next question. Apply least square principle to fit a parabola in given data set. Develop an algorithm for this best fit parabola. To fit parabola to given set of data points using the least square principle, you can follow this algorithm. Input the set of data points x of I, y of I for I is equals to 1 to n, where n is number of data points. Calculate the sum of x values and y values and their squares. The sum of x is sigma xi, sum of y is sigma yi, sum of x squared is sigma xi square, sum of x cubed is sigma xi cube, sum of x fourth is sigma xi power 4, sum of xy is equals to sigma xi into yi, and sum x squared y is sigma xi squared into yi. Now construct the normal equation. So for normal equation, we will construct like this. A is equals to n x squared and as follow, and for v x. This is for y and this is mainly for x. Now solve the normal equation to find the coefficient of parabola. So c is equals to a की power minus 1 into b, where a की power minus 1 represents the inverse of matrix A. Let the coefficient of parabola be a, b and c such that the equation is y is equals to a into x square plus b into x plus c. Output of coefficient a, b and c as the best fit parameter for the parabola. By minimizing the sum of the square difference between the actual y value and the predicted y value of the parabola, the least square method finds the best fit parabola in the given data points. That's all for this question. That's all for this video. Thank you very much.